Okay, we're learning about these bad boys here. This one. What's that? What about that? What about this one? Okay, we're learning about the volume of those solids, and we're looking at cones and pyramids in this video. So they kind of are similar in their relationship with cylinders and prisms. And a quick bit of revision for a cylinder. You recall the volume is pi r squared times h, r the radius, h the height along the perpendicular to the cross section, and that's basically area of the base times height, or the area of the cross section times height. So that's for a cylinder. And for a rectangular prism, volume is length by width by height, which of course is also A times h, because the length by width is the area of the base. On this one, pi r squared was the area of the base. And we're going to look at the relationship of those two formulas with these bad boys over here. For the next part of the video, I'm using a simulation from a website, fantastic website, resource bank, and many other things, called GeoGebra. It's a world unto itself, and I'm using actually this simulation, which is available online, and that's the author there. So what we've got is, it's no accident that the blue shapes are being compared to each other. So we have a rectangular prism there, and we have a pyramid there. Now the height slider bars mean that the shapes are the same height at all times. And the same goes with these red shapes, cylinder and cone. So what I'm going to do is focus on the cone first, and let's have a look. This is not a proof, but it is a demonstration of the relationship between the volumes of these two versus these two. I'm also using this resource here from GeoGebra as well, by this author. And let's focus on what we have here first, which is the cylinder versus the cone. So hopefully you can see on the slider bars where the cursor is, we've got r the radius. So this will control the radius, the first slider. The second one where the cursor is will control the height of both shapes. And t just means I can slide one along, it's translate. That doesn't change the volume, as you'll see in just a moment. So at the moment I've got those settings 0.8 and 3 I should say, and basically you can see that the volume of the cylinder is just over 6.03, and the volume of the cone is 2.01, and if you divide one into the other, we notice that we get 6.03 divided by 2.01, which is 3. Or if you did it the other way around, 2.01 over 6.03, you would get 0.3 recurring, or 1/3. So at the moment, the volume of the cone is 1/3 of the volume of the cylinder. So let's adjust the radius a bit. Change the radius now to 0.9, and you can see that where the cursor is, and we can see that the volumes have changed, as you would expect. Change the radius of the bases and you get different volumes because the area of the base has changed. And we can see that if we do another calculation, we've got 2.54 for the volume of the cone divided by 7.63. And that comes out to with rounding, comes out to very close to 0.3 recurring, which is 1/3. So again, the volume of the cone is a third of the volume of the cylinder. What if we change, instead of the radius, what if we change the height? So we kept the radius the same. I'm going to change the height, reducing it down. And just to show you that the radiuses are the same and the heights are the same, you can put that in there, see it shows it. Okay, so let's go 1.44 divided by 4.33. See if we get a third again. Yes, we do. Okay, so that's a third. So the volume of a cylinder is 3 times the volume of a cone, or in other words, the volume of a cone is a third of the volume of a cylinder if you've got the same height and radius. So returning back to the other simulation, we can see that if we've got the slider bars show us that the heights and the radiuses for the shapes are the same. So the two circular, the curved solids, they have the same radius and the same height, and basically the side lengths, or length and width, of the prism and the pyramid are the same, and their heights are the same. So let's see if they give the same relationship as before. So if we've got 32.72 divided, I'm doing it right now as I speak to you on my calculator, 98.17, and yep, that comes out as a third. So the cone has 1/3 of the volume of the cylinder. We can do that too. I mean, you can, while you're watching this, you can do these same calculations to check it yourself, and same with that too. So it suggests that both pairs of shapes have the same relationship. The volume of a pyramid with the same base is a third of the volume of a rectangular prism, and the volume of a cone with the same circular base and height has the 1/3 the volume of a cylinder. And we can experiment further if we want to, but the relationship comes out the same. So if you're stretching out the circular shapes, these will happen, and you can see the results change. You can pause it at any time and test it out yourself, or likewise with the other two shapes too. Okay, so I'm adjusting both, and you can see the calculations change. You can try that yourself. So formalizing that, the volume for pyramids and cones is a third of A times H, where A is the area of the base and H is the perpendicular height, not the slant height. Now that alone is the A times H, remember, is the volume of any prism or cylinder. So it's 1/3 of the volume of a prism or cylinder. So three variations appear there. They're not the only ones, because notice how pyramids come with all different types of bases. That one is a square base pyramid, but you can have rectangular base and polygon bases there. So for a right square prism, right means that the perpendicular height is like that, right inside the guts of the pyramid, and it goes straight up, of course. It's not on a slant or an oblique one. So there's 1/3 area of the base times the height, and if the side is length x, it'd be 1/3 x squared times h for a side length of x. For a cone, same formula, and then the h is different. It's pi r squared because it's a circular base, and that's for a right cone where you have the vertex straight above the center of the circle. You can get slanted or oblique shapes like this if you know the perpendicular height. Sometimes you might need to use Pythagoras to find that in some questions, if you're given the slant height, for example. but you need to use the perpendicular height. If you know the area of the base and times by the perpendicular height, you can apply that the same. Let's look at one final example. For this pyramid here, it has got a rectangular base, so it's different to the ones we just saw a second ago, but not really, because the formula is the same, 1/3 of the area of the base times the height. So we've got 1/3, the area of the base, well, the base is a rectangle, so it's 1/3 times the length times the width of the base, 1/3 times 1.4 times 1.2. We know the perpendicular height is 1.3, so we sub that in there and we crunch that. We get 0.728. Now, meters are the units, so the volume will be cubic meters.